Okay, now based on my graph, which is not great, but we can still get a pretty good estimate. And I can put this into Excel. I can put these numbers into Excel and get the very best fit. Okay? But it's going to be close. Okay? So this is y equals mx plus b, but it's now x equals mt plus b, because we don't have x here, we have x here, right? X is where y is supposed to be, t is where x is supposed to be. So we got x equals mt plus b. B is the y-intercept. Well, people back there think it's around 30, and I think it's around 30, so 30 is a good estimate. Okay? And what's the slope? Well, it looks like the rise is negative 30, and the run is close to 200, right?
Yeah.
Mm-hmm.
And 30 over 200 is 0.15, so it's about negative 0.15 t plus 30. You plug any one of these t's into that function, if I did it right, you should get a number very close to this. Okay? That's what we mean by a linear function and a linear model. And I assume everybody knows how to do that, but if you don't, well, I just gave you an explanation, and if you need a bigger one, we'll see tomorrow. We'll give you one, okay? But that's pretty much an Algebra 1 exercise. So if you think about the equation of a straight line, review that a little bit, it'll be clear. Look it up on the internet, Khan Academy, whatever. Whatever you need. Okay, so there's your linear model of range versus clock time. Now we have a quadratic model. And this is really where energy conservation in physics gives you this. And then knowing that this has to be the rate of change of this, we know this has to be linear. And you don't have to understand that, okay? So what we're doing for the depth versus clock time model, we're going to do something very close to what we did with the pendulum, okay? This is a quadratic model, and the model is going to be y equals a t squared plus bt plus c. Okay? Now, in order to get, well, how many equations are we going to need? What are our parameters? I'm using a word that you just heard, so don't feel bad if you don't understand what I just said, but I'll make it clear. What are our parameters here? What are the things we don't have information for? A, B, and C, right?
Yeah.
Okay? Now, we could just pick 3 of these. You know, 28, 150, 103, 53, 172, 12. Plug them in for y and t, and we get 3 equations, wouldn't we?
Mm-hmm.
Okay? Oh, that would totally ignore the rest of our data and totally ignore the fact that there's a trend to our data and that any data point, any single data point has more error in it than the general trend will. Does that make sense?
Mm-hmm.
Okay? So what we want to do, and don't have time to do before lunch, we'll do this right after lunch and when you're all fresh and ready to do things. We're going to do a graph of this data, even though there's a flaw in here somewhere. There's just a horizontal translation of the graph that fixes it. Okay? As soon as we figure out what it is. So what we want is we want a graph of now y versus t. T conveniently goes up close to 200, so we'll put 200 here and subdivide that accordingly. Y goes up to 150. Well, 160 is easy to subdivide. So put 160 here and 80 here and 40 here and 20 here and 10 here and subdivide the rest of the intervals, right? Mm-hmm. In the obvious manner. And then we're going to get a graph that's probably going to look something like this. okay? And then we're going to take 3 points on the curve that we think best does the trend line. Now that curve is not going to wobble around to get from one point to another. It's not even going to try to go through any point. It's going to go through what you think the real trend is, and it's going to be a nice, smooth, parabolic curve. Okay? So we're going to do that after lunch.
All right.
Fair enough?
Mm-hmm.
Okay, take a break, get some lunch. Have a good time. And back here at 1 o'clock.